special distinguished lectures, and indeed the last two distinguished lectures in the series deal with earth and environmental science. It's a great pleasure to introduce a colleague and a friend of long standing, Dr. Susan Kiefer, who's now at the University of Illinois. She's had a very varied and interesting career. We've known each other since we were both graduate students or postdocs and really have collaborated on various things. Sue is trained as a geophysicist, and her interests have really, and contributions have really been very eclectic. They've ranged from mineral thermodynamics, in which she's done simplified models of the lattice vibrations in complex solids, and that was where I first got to know her, and indeed we co-supervised a graduate student, to thinking about fluid dynamics, thinking about what happens in rapids on the Colorado River, to thinking about what happens in plumes that come out of the outer planet, planetary moons, for example, Enceladus, to many other problems in geophysics where the physics, the chemistry, the fluid dynamics all come together. And she's similarly had a varied career in terms of locations. As I mentioned, she got her PhD from, or I didn't mention perhaps, she got her PhD from Caltech. She spent many years at the U.S. Geological Survey in Flagstaff, Arizona, a place where they trained astronauts, among other things. Sometime at Arizona State University, sometime at the University of British Columbia, sometime after winning a MacArthur Fellowship in Canada, doing various things in science education and other things, having her own company for a while, and then the University of Illinois. She and her husband have now bought a house on Whidbey Island in the Pacific Northwest, and that may be the headquarters for some interest in geophysics for years to come. Sue is also a member of the National Academy of Sciences and has served on many government committees and so on, looking at various areas of science and active areas of science and policy and thinking about education. And she's also a pretty darn good musician. So having said all of that, she's going to talk about natural and man-made, if you will, disasters, and what she particularly calls stealth disasters, and really emergent phenomena in how these things happen. Sue.
Coming out tonight. I've had the good fortune of having 6 wise men in my career for at least 20 years. I call them my wise old men because they are all men, they are all old, and they are all wise. And they refuse to be co-authors anymore, so this is how I'm acknowledging them. And we've done various things of organizing symposia, writing papers on some of the issues of societal concern that don't really fit our traditional roles as geologists, but that we can't avoid seeing. I don't work on emergent phenomena as such, and so when Alex asked me to talk about this, I had to think, and she can talk anybody into anything. So this is a brand new talk for me, actually, and it gave me a chance to think about some things I've been working on in a new light. And so I'll tell you that I'm actually sometimes more comfortable talking about lots of equations and things than I am some of these ideas that I'm presenting, but they're speculative and they're meant to stir discussion, so I hope you'll take them in that spirit. So I'm going to talk about how I'm going to use the word emergent phenomena, and then I'm going to talk about natural disasters, and I'll define that using volcanic eruptions and earthquakes as examples. And then I'm going to define stealth disasters and talk about a couple of those, some problems when you dam rivers, when you deforest, and problems with soil. And then I'll talk about my conclusions and speculations. Now, I'm not going to talk about a whole bunch of hazards that fall under this category. Man-made hazards such as nuclear warfare, bioterrorism, nanotechnology gone wild, Alex. And I'll point out that if you are interested in things like that, there's this book by Posner who talks about a lot of these phenomena. Volcanic intrusion into a nuclear repository is actually something I did a tiny bit of consulting on. And then there's the, especially at the University of Illinois, I get a chuckle when I mention the high energy physics experiment that might go awry. And don't ask me how, it's in Posner's book. And then there's some natural things I'm not going to talk about, including outbursts of charged particles. And when I gave this talk as a practice run to the geology colloquium at Illinois, it was like 2 days after a major solar outburst. And so I'll just point out that a solar flare and charged particle event. I lost the name of it. But this year and next year, are we coming into a solar maximum? And you might want to keep your eye on some of the phenomena that happen, because we've got a lot of things out in space and in our electrical grids that are potentially affected by these. And I'm not going to talk about big supernova explosions or big meteorite impacts, because we won't be able to do anything about those anyhow. So I'm going to use the term emergent phenomena in the sense of complex patterns that arise out of relatively simple interactions, and that the result of local interactions between individuals or agents leads to something that emerges at a bigger scale. And in particular, I'm going to use the concept of a tuning parameter. And that is some quantity which, when it hits a critical value, the system behavior changes rather dramatically. And the popular books, for example, that you might have heard of on this recently are The Tipping Point by Malcolm Gladwell and The Black Swan by Nassim Taleb. So the basic idea of this is that you have agents or entities that have rules that interact, and that creates something else at a bigger scale, but it then has different rules of interaction that leads to new entities, and you cascade up the chain like this. So atoms interact to form molecules, which interact to form cells, which then end up forming organisms. And this word, as I think you've seen in the way this course has been designed by Alex, there are different characteristics and uses of the terms in different disciplines. And so where I come in is this talk is a blend of how we look at natural disasters in geology and stealth disasters more in a social science sense. And when I was doing some research for this, I actually came across some really interesting literature in the military literature about warfare as emergent phenomena. And is it inevitable? Are there characteristic timescales? And there's some really interesting reading there that I certainly never got into in my geology career. And so when I thought about this talk, the question was, does looking at natural disasters through the lens of emergent phenomena actually teach us anything useful? And that's the question I'm going to try to come back to at the end of the talk. Because if it doesn't lead us to anything useful, then this has all been an academic exercise. And a couple of weeks ago, I didn't know what the conclusion of this talk was going to be. So it could have ended up as an academic exercise. So I'd like to give you an example of emergent phenomena using ant trails. And this is simulation with NetLogo. As I said, I've never done emergent phenomena calculations, but I really enjoyed getting into this and playing with it. So the idea in this problem is, it's a very simple problem. You have an ant nest in purple, you have 3 food piles in blue, and you have ants in red. And when an ant goes out, he leaves a scent on the ground, and that scent can disappear in 2 ways. It can either dissipate into the ground or it can evaporate. So those are your 2 control parameters. And then this just gets plugged into a simulation, and you find that if you have some extreme values of these parameters, model 1, where your diffusion rate's 50 and there's no evaporation, or in model 3, where your diffusion rate's 50 and there's a lot of evaporation, the ants can't find the food. But in model 2, where you've got these intermediate parameters of 50 and 15, the ants can find the food piles. So then you go play around in this more restricted range of parameters of model 2 and find out that there's actually 3 ways the ants can be eating. They can eat 1 pile, 2 piles, or 3 piles of food. And it's all very sensitive to the values of these parameters, whether the ants find food or not. And I really recommend this NetLogo because I'm not all that computer literate anymore, and I found it easy enough to get in that I could just change a few things and pretend I was doing something myself. Well, the problem is that was complicated when you only had two parameters, which were the diffusion rate and the evaporation rate. So you take something like another example in that logo, where you've got wolves and sheep and grass. You've got things like, is the grass going to regrow and what's its regrowth time? You've got your initial sheep number, how much the sheep gain from food, and how fast the sheep reproduce. And you have your initial number of wolves, and how the wolves gain from the food, and how the wolves reproduce. And you get an incredibly complicated array of possible results. So my hypothesis is that many kinds of disasters emerge from the behavior of individual humans, which are the agents in this jargon, and that the tuning parameter is the human population, and that at some critical value of the human population, things may change dramatically. I can tell I'm in California because it's gotten dry. So here's how I'm going to define my disasters. And there's a continuum between these. So I take a natural disaster as what used to be called, or maybe still is, by the insurance industry, an afterthought. So it's natural. It happens pretty much in that non-bio part of the world. But it can be amplified by human behavior. So a flood in the Sacramento Basin here may not have been a disaster until humans started living here, and our behavior exacerbated that. Typically, natural disasters have a fairly sudden onset and immediate consequences. They make great newspaper headlines. There are historic examples, and remediation and recovery are often possible. So, in contrast, I'm saying a stealth disaster is caused by humans, but involves the natural systems that support us. They often have gradual onset, so they don't make newspaper headlines very easily, but they have near-term consequences, years or decades, or centuries. And they're new to human experience, at least at a global scale. So if you're on Easter Island or any island society, you may have experienced these stealth disasters simply because you have finite resources. And the population can grow to be such that you use up your resources. But we're now in an era where we really are in danger of exploiting all of the critical resources of the planet. And in this case, remediation and recovery may be questionable, and these stealth disasters may lead to collapse. And there's Jared Diamond's book on collapse is very famous. There's one I like better because it's about a quarter the length, by Joseph Tainter, and it's called something like Collapse of Complex Societies. It's a really nice little book. So let's talk about some natural disasters historically. This is a chart of volcanic eruptions. They range in size from this one, which I've actually seen, 1 cubic meter that was erupted from a steam well in Iceland when a volcanic dike, a sheet of magma came through and happened to hit the steam well, and the lava came up the tube, and you had a cubic meter eruption. More relevant, there's Kilauea that erupts in Hawaii once every several months. Mount Etna, up to 1/10 of a cubic kilometer every 5 years. Mount St. Helens in 1980. Pinatubo in 1990. Krakatoa in 1883. And Tambora in 1815. And so here, we're down here, you're down here. Our grandparents tend to be in here. And my question was, what does the yellow box represent, if we look at the dates here? Anybody have a guess right away? It's the Industrial Revolution. So just since the steam engine was invented, these are the volcanic disasters that we've had. And on this slide, you can see the relation between what I'm saying about volcanoes and what we are seeing with population. So here's, I think the 1790s taken as the beginning of the industrial age. We've had, these are called volcanic explosivity indexes. They range like a Richter scale in earthquakes from 0 to 10. So 6 and a 7 is a fairly big but not the worst kind of eruption we've had. So 10's, where'd it go? Sorry, I'm going the wrong way. Okay, tense would be Yellowstone, Hollywood type scale of eruption. Well, the reason I'm pointing out that the Industrial Revolution was important is that it's come at a time when we're really ramping up in this exponentially increasing population. The increasing density of population creates an increased density in the social fabric. So you're tied together, you have a society that's tied together globally now, and an Earth that is going to keep on giving you this VEI 6 and 7 volcanic eruptions. And the point of this is that the consequences of those eruptions are changing because the interconnectivity of this society is changing. Well, what are the effects of volcanoes on humans? Well, if you're real close to the volcano, you die, you get buried in ash, your roof collapses on your houses, you lose your shelter. Further away, the food crops are affected. Particularly, we see this in Central America a lot. Water is contaminated, weather is influenced, and climate is actually affected. And there are people who will point out that the sulfur aerosols produced by volcanoes are counteracting global warming. That's one of the arguments you'll hear. Okay, so let's look at an example. Here's Laki in Iceland in 1783. It was only a VEI 6, so it's not a huge thing. Erupted 14 cubic kilometers of lava, but it was a very sulfur-rich lava. And it dumped aerosols into the atmosphere for 8 months. It also had a lot of hydrogen fluoride. And the local effects were that basically 80% of the sheep, 50% of the cattle and horses died from fluorosis, and 25% of the population of Iceland died from this eruption. There was a 5 degrees centigrade cooling in Europe. There was severe extreme weather, poverty, and famine, and there's credible speculation that this event fed into the French Revolution in 1789 because of the social unrest and disorder. And in North America, there was very severe winter, and I, of course, had to do this since I'm from the Midwest. The Mississippi River froze at New Orleans, and there was ice in the Gulf of Mexico. The Tambora eruption in 1815 was a VEI 7. It erupted 160 cubic kilometers of magma. This is just 200 years ago. The local effects were the usual. 10,000 people were killed by these dense hot ash flows that we call pyroclastic flows. The global effects were that there was a year without a summer. The global temperature decreased about a ½ degree centigrade. 50 to 60,000 deaths by starvation and disease. And there was a severe typhus epidemic in Southeast Europe and the Mediterranean between 1816 and 1819 that was attributed to these weird climatic conditions. Krakatoa you've probably mostly heard of, so I'm not going to go into it, but it was just a VEI 6. It erupted 25 cubic kilometers of magma and it caused 36,000 deaths, mostly by the tsunami that it produced. And then, more recently, Pinatubo and Eyjafjallajökull. Pinatubo was maybe before a lot of the students were born. It was an eruption of the Philippines. This eruption could have killed tens of thousands of people if it hadn't been one of the most successful prediction, monitoring, and preparedness efforts by the geologic and the civilian defense and military defense communities. Destroyed 150 square kilometers of forest, 800 square kilometers of rice-growing farmland, 800,000 head of livestock and poultry. I couldn't convert 1991 pesos to dollars. That's what comes out of Google, but I don't think that's the real cost. And the global temperatures were down by about 0.4 centigrade. Now this one you probably all have remembered, and maybe were even inconvenienced by it. This was a very tiny eruption in Iceland, by Icelandic standards. 0.14 cubic kilometer of magma erupted. 107,000 flights were canceled, costing the airline industry something like $1.7 billion. Europe, the supplies of essential goods were completely disrupted because of the importing. Africa suffered major losses because they provide flowers and vegetables and food to Europe. In Asia, there was a disruption in supplies to the automakers, and in Australasia, no fish were imported from Norway. So you can see these effects just going around and around the globe. And that's what the interconnectedness is doing to us. Well, I decided I had to play with NetLogo to have any credibility on talking on emergence. So I turned the, I forget which problem this was, but oh yeah, this is the typhus epidemic. So I pretended there was a volcanic eruption here, and a typhus epidemic was spreading out, and there's some rule built in to the contact and what it takes to spread this disease. And so this population density varying just from 58% to 60 to 62%. You get basically no spread of typhus to some spread to completely wiping out this grid. These are very simple problems, but it gives you it's really fun to go in and play with this and see how sensitive it is to your assumptions. Do you want to say something?
It was just rather depressing.
Yeah, it is. It really is, especially with this flu epidemic going around Davis right now. So I just wanted to touch on earthquakes because there are some big ones ahead. In 1556, an earthquake in Shanxi, China left approximately 800,000 people dead. It's hard to know that. People were living in houses and caves carved out of the windblown lust, it's called. It's windblown dust. And these just collapsed completely in this earthquake. Another one in 1976, 250,000 to maybe 600,000 people killed. We rarely can get good statistics out of China. Repeatedly, we have earthquakes in these other places that I've listed: Iran, Japan, Turkmenistan, not so much Japan with major deaths, but that kill tens of thousands to hundreds of thousands of people. In the Tohoku earthquake a year ago, actually fairly few people died because of the earthquake, and the building codes are really good there. But so I shouldn't have Japan on this list. I wanted to make the point that they occur repeatedly because they really enforce building codes in Japan. So coming to where I live, I was telling Alex that I don't like tsunamis at all, so I'm happy. I live a kilometer from the South Seattle Fault in this region, but I'm at 400 feet above sea level, so I can deal with earthquakes, but not tsunami. In the Seattle region, it's possible there's going to be a magnitude 9 earthquake. The last time that happened, it's actually well documented because the tsunami was recorded in Japan, and there's a real beautiful book that's written about the reconstruction of this orphan tsunami by Brian Atwater. There may not have been any people or very few people living here. The population today at risk is 3 million people. The 1906 San Francisco earthquake was a magnitude 7.7 compared to the Tohoku, which is a magnitude 9. And there were 700 to 3,000 killed out of 400,000 population, and today the population is 7 million. One place I don't want to visit until the earthquake gets out of its system is Istanbul. The Eastern Mediterranean gets an earthquake pattern that Amos Noor called earthquake storms. And these quakes are just marching right up the Anatolian Fault toward Istanbul, which has a population of 6 to 9 million. Which had a population of 6 to 9 million then. The current population is greater than 300 million, will be 400 million in a few years, 10 million in the city itself. And the USGS has put out that an earthquake of magnitude greater than 7 or 8, a 60% chance of that occurring by 2030. And then just before I prepared this, the Japanese revised their prediction for a major earthquake around Tokyo and say now that it's a 70% probability of a magnitude 7 quake. I think that's within the next 10 years, I'm not sure. a 98% probability within the next 30 years. Why the new prediction? And this is actually an important part and a point of my talk. This is an example of how a society is updating models with new information. And this is an essential activity for systems that have emergent phenomena. So they've determined that the change in the stress field during the last earthquake, the Tohoku earthquake, has now changed the chances of an earthquake around Tokyo. Okay, so conclusions about this on natural disasters, that we are in a world that has constantly changing geologic conditions. They can be gradual changes or they can be catastrophic. Their impacts on human and our civilization will be much larger and possibly unexpectedly different in the future than they have been in the past. And that these are characteristics of emergent phenomena that have a tuning parameter that's the population. We're simply putting more people in more places at risk with more interdependence on each other and our resources. Okay, so on to stealth disasters. This is pretty discouraging stuff. The first example I'd like to do is talk about what happens when we dam our rivers. I've worked on the Colorado River and the effects of Glen Canyon Dam on the river through the Grand Canyon. There's 125 years of work on the Mississippi system, but on the Nile there's 7,000 years of significant human manipulation. And the lessons that have been learned from this are applicable to major rivers that have levees and dams worldwide, but we keep doing the same things over and over. So the Nile had an early population of about 1 million concentrated in the Memphis and Thebes area. And there's some speculation that the decline of the Old Kingdom in 2200 BC was due to manipulations on the Nile. Back then. They started constructing the Aswan dams in the late 1800s, and now there's a population of more than 60 million people. And the lessons that you get from looking at any of these systems that have been dammed are that the whole ecosystem has, and everything including the humans in it, have been altered, and usually not in ways that are in balance with how the planet works. So by controlling the Nile and eliminating the floods, the Egyptians lost the replenishment that goes along with the fresh sediment being brought in by the floods. That triggered the need for more fertilizers, and fertilizers contain toxic chemicals that then get concentrated by their use. We see this in the Midwest too. You have pockets of stagnant water, particularly on the deltas, and these have led to the reemergence of some severe diseases. The loss of silt and algae downstream of the dams has caused a decline of the sardine resources and shrimp from the Mediterranean. In the Grand Canyon, it's resulted in the loss of the beaches because it's just an erosive regime all the way through the through the Grand Canyon. And the loss of fresh water has caused fauna from the Red Sea to migrate through the Suez Canal into the Mediterranean. And you can go on and on. At other places in the system, you'll have problems with sedimentation. You get cultural dislocations. This is a big issue with the Three Gorges Dam in China. And you get major changes in your ecosystem. So I'd like to move on. This is a case I had not heard about until a geologist named Peter Huntoon came through Illinois and gave a talk about the deforestation of southwest China. These three provinces in China are amongst the poorest. In fact, there's major drug trade from Laos, Vietnam, and China goes, Vietnam, Laos, Burma, goes through these three provinces. And they are populated by ethnic minorities. So there's some social tension too. This whole region of China is underlain by limestone, which forms a topography called karst that comes from the water dissolving the limestone. You get Mammoth Caves, the big cave country is in this. And that's resulted in these beautiful pillars. And Peter was telling about traveling through China, and he was hot and sweaty. He realized he was in a tropical climate and asked why there weren't trees. And basically had discovered this whole phenomenon himself. When the Great Leap Forward came in 1958, Mao ordered the modernization of China to make steel, and they needed the trees and wood from here to make the steel and run these blast furnaces. And so enormous, they dug up everything, tree stumps, and you have to be desperate for wood to want to dig up a tree stump to burn it. And unfortunately, there were 3 phases of attacks on these forests in southern China. There was the Great Leap Forward, there was the Cultural Revolution, and then when the people came out of the collectives into the forest, they again deforested them. And the result was that the green, what's called the green reservoir that was holding the water in this karsti topography was gone. And the groundwater that was then stored in these forest hills just went away. Groundwater dropped. The normal flood and drought cycle was exacerbated. They had drier, hotter, dry seasons resulting in desertification. And this is a picture of the women. Women do all the work here, carrying wood for very long distances to bring it into this area. But there are no trees on these hills. And then the third stealth disaster I'd like to talk about is our soils. Malthus made the prediction that since our general resource supply was linear, our population increase was exponential, that we were going to have a food crisis. And I can't remember the exact date, it may be on the next. And we've managed to avoid it. Okay? It has not happened, and there are a whole lot of people that say it'll never happen because human ingenuity will win. And so the reason that we have avoided it so far is that after World War II, we had a major increase in the use of fertilizers and energy intensive technologies. So we've been able to greatly increase our production of corn and soybeans, but at the expense of, and by the methods of these highly energetic and toxic farming practices. Well, the point is that soil fertility is determined by, natural soil fertility is determined by geologic processes at geological timescales. And I put in this map up here because I'm actually a dual citizen with Canada. And so when I'm up wearing my Canadian hat, I point out that we Yanks stole all the soil from Canada, the glaciers. Just stripped it off Canada and brought it down here. So we have a fantastic gift, when I have my Yank hat on, from the Canadians of all of this soil that was shoved down on us. There's no more up there. And you don't have to drive very far north in Canada to realize that once you run out of their fertile country here, there's nothing left to grow crops on. And it's not going to come back on human timescales. So we should be taking good care of this soil. So there's a geologist named Roger Hooke who has done an inventory and shown that humans move more soils than all the rivers in the world. And we may move them by factors of 2 and 3. It's not trivial. We really are giant soil movers. Agriculture uses 70% of the world's available fresh water. It impacts the global erosion cycle, river systems and oceans. Removes the chemical elements 1 to 2 orders of magnitude faster than nature can replenish them. And basically affects the whole planetary geochemical cycle. And the major conclusion I'd like to draw here are this massive dependence on fertilizers was possible because of the cheap energy from fossil fuel after World War II. But there are serious consequences. Nitrates contaminate 1/3 of the groundwater resources in southern Ontario. And we have the anoxic zone in the Gulf of Mexico where nothing can grow because these fertilizers are down there feeding the algae. Is it the algae that are causing the bloom? So if you can find many different versions of this, but this is a map of very degraded and degraded soils in the world. And you can see that a lot of them are degraded, including our whole Midwest corridor of the Farm Belt country. And I saw a picture once that I've never been able to find, but it was a picture of an old farmhouse in Kansas, and that had stood for probably a couple hundred years. And the base of the doorway was about this high. And that's a measure of where the soil used to be naturally, and a measure of how much compaction we've done to our soils in the Midwest. Forget the fertilizers and anything else. We compact them and they blow away, eventually. Okay, well, I've only covered a few stealth disasters. You could probably add some, but here are things that I think we ought to be watching. Our fresh water quality and quantity in our rivers and lakes. Deforestation, the soil quality and stability, air quality, climate change, atmosphere and oceans, acidification, biodiversity, desertification, and there's probably more that I haven't put on this list. I keep forgetting I can use this. So my hypothesis is that the world of geology plus human beings is a complex system, that many kinds of disasters are resulting from the behavior of us individual humans, the agents, and that tuning parameter is the human population. And my hypothesis is that stealth disasters are emergent phenomena because a critical value of the tuning parameter has been exceeded, and that is the carrying capacity of a region or of a planet. Now, this could lead to a whole discussion of who thinks how many people the Earth can support, and there's a big literature out there, and you'll get numbers that range dramatically. And furthermore, for many of the natural disasters in the past, I think the population was below the critical value of this tuning parameter. But this is unlikely to be true for a number of the disasters in the future. So then I come back to my question, well, so what? Are we learning anything by this exercise? Well, here's what I see as the problem, that the actions of us individual agents lead to the emergent phenomena. But these often occur in distant places, so we're not affected by our actions, or they occur at a future time, and we have a knack for discounting the future. It's hard to get people to care for 10 generations from now. 1, 2, maybe, 2 maybe, but this is called discounting the future. And so, this is a famous quote by Churchill: "Those who do not learn from history are doomed to repeat it." The question is, how do you learn from the past in complex systems? And so I thought, I was working, so I thought, well, if those ants can learn to find food, we ought to be able to learn something from this. So the conclusion of what do? You need to change the behavior of the agents. They, in turn, need to change their interactions with people they interact with. And so you have this perturbation, and this perturbation can grow, it can die out, it can become a movement, or it can grow exponentially. And if you're reading the emergence literature, one thing came out that is inescapably unpredictable. I think that's a really good phrase, if you can say it. So I cited the example of the French Revolution, the events of 9/11, the Occupy Wall Street movement, Arab Spring, the financial meltdown of 2008. These were all kind of that emergent phenomena manifestation. So one of the lessons is we have to have a continuing developing awareness of what's going on in order to cope with new phenomena that nobody could have predicted. And so the models of the effects of natural and stealth disasters must be based on databases that can allow for changing interactions of the agents. And I include in that, here I was with some of the people on my first slide interacting, we can't even assume that our political and economic systems are static, and we tend to make that assumption all the time. I also think that reductionist approaches to understanding the impact of future natural disasters are unlikely to be productive. You just can't you can't treat this like a physics problem. And I say I do have an undergraduate degree in physics, so I'm not putting down physics. It's just, I think that we need this kind of emergent phenomena, complex system approach to these phenomena. And these phenomena are multi-level structures. There's nested levels. So I think we can study the lower levels to determine statistically expected emergent features, and we can study the higher levels, that is the phenomena, the disasters, to try to infer interactions at the lower levels. And I think that in the future it might actually be helpful to view natural disasters from the perspective of emergent phenomena, because we tend not to do that. We still treat them in a very deterministic, reductionist way in many cases. And so I just thought for my concluding slide, I'd put up the schematic instead of leaving a bunch of words up there, and hope that we can have some discussion. So, discussion, questions?
Well, so I think it's an interesting example to look at the stealth disasters through something like Malthus's prediction that we're going to have a food crisis, and identifying that through the implementation of fertilizers we were able to increase the food production. But of course we also have issues of leading to monoculture that harm biodiversity, and we have runoff that contaminates groundwater. So digging into these kind of more and more complex systems, the more alternate changes that we make to the landscape, it seems the higher the level of complexity evolves. And so I wonder if you have a kind of outline of this sort of multi-level approach, and how much room is left for kind of real-time monitoring of updates that we can be putting into these models to notice how immediately we're changing things, and how best we could predict what those changes might bring about in specific environments.
Yeah, I had one of the things I've thought about is I think it's related to that. And it seems to me that we really need sort of a world order, right? You could call it, pretend we're an island instead of using world order because it sounds political, but I sort of envision that we need 4 bodies that we actually don't have at the moment. We need a scientific body that can keep doing kind of what I'm doing, that will do that monitoring, thinking of the theories, trying to understand what's going on. We need an engineering body that can actually address and solve the problems practically. We need a political body that can deal with all the different cultures and values oriented. And we need an enforcement body. And there are pieces and parts of these, and I actually have another slide, not tonight, but I've thought about this. So you can cite parts of the United Nations, you can cite parts of the US Geological Survey, or that, but they're all just pieces and parts. And I think that without that, because of this problem that the effects happen for most of us in the first world countries, they happen at a distance. That without having something that makes them real, both in space and time, it's too easy to do nothing. And you know, I believe in recycling paper, for example, but it doesn't accomplish a lot unless there's sort of a critical mass, a tuning parameter in that particular sense. Did that answer what you were asking?
Yeah, I think so. I mean, I'm just kind of wondering about, sometimes in our discussions about addressing the emergent situations, the question comes up, how can we predict for something that is emergent? And so I like the idea of the tuning parameter, because this gives us at least something to track, and gives us maybe predictable outcome. But I mean, that seems to be one of the major conflicts with any approach that's emergent, is I don't know the outcome. So
right, that inherent unpredictability. Right. The interesting thing about the tuning parameter being population is that you immediately get into, well, how many people can the planet hold? What's the critical number for that tuning parameter? Now, on this slide, this was a very simple problem. So, yeah, it's right there at, whatever, 60%. But it's a lot harder to set that if you don't even know whether you're coming up against a limit. And there's a lot embedded in economic theory that assumes there are no limits. And if I've never had an economics course, but I would love to just study that and try to figure out how you factor in the limits. And you pretty soon get people philosophically butting heads.
So another phenomenon is the disasters that didn't happen. A good example was all the fear of the bird flu epidemic of whatever, 3 years ago, and the responses of the Chinese screening everybody at airports, etc. And somehow the transmissibility did not happen, and then a prediction gets a bad reputation, or if we can begin to predict earthquakes, but only with a certain certainty, at what point do you warn a population? So what are your comments on that sort of thing?
Well, you can see that actually the bird flu thing is very interesting. If you think you're in this regime and you end up there, the public's not going to have much faith in you because we prepare for this, but this is what happens. And yet you can see it's very sensitive to your interactions. The problem of warning the population is enormous. And I don't know, have any of you heard about the Italian seismologists who are on trial? The geophysicists people have. There was a town called L'Aquila in Italy that is having a lot of tremors. And there was a person in that town who was monitoring radon and found there were increased levels of radon, and it started publicizing, oh, there's going to be an earthquake, oh, there's going to be an earthquake, and the public was panicking. The Italian government sent in 6 of their most prominent scientists and 1 government bureaucrat to evaluate the system. And it turns out that the whole thing was probably a setup. There was a predetermined conclusion coming out. They went in, according to what I've been reading, had a meeting in which they didn't actually have much information, came out, the government person said, the equivalent of there's not going to be an earthquake. I'm not quoting it accurately, but if you Google Italian seismologists trial, you'll see this. There was an earthquake a week later, and quite a few people were killed. So the Italians have charged these scientists and the government bureaucrat, and now there's a second person that's been involved with manslaughter. And it's very complicated, and it's got the whole hazards community on edge because we're always dealing with probabilities. And that's very hard for the public to understand, even in the best circumstances. But when it gets a communication snafu like this, it's very serious, and these people could be in jail. And it's a system where I think there's just one judge that is trying the whole case. So it's been a big issue in science. It's covered in both Science and Nature journals.
No, I'm surprised you have such a simple tuning factor as the population. And it's usually what you need to get at is to sort of identify or categorize different types of tuning factors. And then look at the interactions of those, because the problem is so complicated. You need some mechanism by which you organize your thinking. And by sort of categorizing tuning factors, it seems like it would be a way of starting to look at it more analytically, and that sort of has a sort of a repetitive way of thinking about it. So like just choosing population, it seems too isolated. I mean, it seems is obviously a main driving factor, quote tuning factor. There must be other variables in other categories that are behaving in comparable kinds of ways. So that when you're thinking of an emergent system, it's really the interaction. How do these different kind of categories and their characteristics interact to give you emergent behavior? Have you thought about that? I mean, if you
Well, my thinking is pretty new on this because of giving this talk.
Yeah.
If you go back to that grass, sheep, wolf,
Yeah, that's good.
I mean, you could say, okay, there's 3 tuning parameters. There's the health, and I just didn't try to do that for this talk. But no, you're exactly right. And there's a whole formalism actually for doing that statistically, and I forget what the jargon is. It's It's sort of a fitting, it's a landscape fitting parameter, something like that. Now, I think though that the basic assumption in this talk is that population is one of the strongest tuning parameters. And I probably should say that up front. Because clearly if we had abundant resources, abundant grass in that, you come to a different equilibrium than if your resources are scarce. Jared Diamond had a sobering conclusion in his book on collapse, which was we've got a number of these disasters out there. He didn't use the word stealth disaster, but his point was that we have to solve them all. Because if we miss one of them, it's likely to get us. It's a complex problem, and it's largely, I think, more a social science problem than a physical science problem. It's human behavior. I mean, we have known since the Egyptians what happens when you dam rivers, and we keep going on and damming rivers. We somehow think we're always going to be smarter than we used to be.
Another sobering thing is that all major civilizations seem to go through a period of growth followed by a period of either decline or sudden collapse. So are we different?
And Taylor actually addresses that really nicely in that little book, The Collapse. He defines complexity in a way in that book. It's quite, and it was a surprising find for him. He's in the U.S. Forest Service in Albuquerque.
What was his name?
Joseph Tainter, T-A-I-N-T-E-R. I've read the book. He puts everything in terms of diminishing marginal returns. And I had to struggle with what that meant. But he actually includes examples of NSF funding levels, and when are you in diminishing marginal returns in that game? Universities that try to support themselves on research funds are dealing with diminishing marginal returns.
Yeah, we're talking about collapse of systems and sort of these tipping points. And I wonder if there are other kind of tipping points that actually can do just the opposite, can reverse a collapse and prevent a collapse, or in fact, reverse the cycle entirely. And one that comes to mind is Fukushima. I mean, after that disaster, and that Germany, and made a unilateral decision at the highest levels of government to do away with nuclear power.
Yeah,
And they have absolutely no, I mean, here you have a country that relies on it. They don't have a strategy necessarily, except the recognition that they have the prowess to find alternatives. And they saw that also, I think, and my interpretation is they also saw that as an opportunity, because the world has to move in that direction, that if they force their society to find alternative energy, that in fact they have to develop the technologies to do that, and they'll be in the forefront of it, and economically that will be beneficial down the road. And you wonder whether a move like that, maybe that's a small one, but it's a big country and it drives Europe. I mean, whether that can shift, that kind of thing can shift the tide, and whether that is that's a tipping point that can move us, in the opposite direction to prevent these sorts of things. But it only happens when it doesn't happen over a protracted period of time where you have these long debates, we continue to do stupid things, but it happens when you just make a split decision that you're going to stop doing something overnight. And that's what Germany has done. It's an interesting phenomenon.
Well, it is, and it's, I mentioned that you can have, if you change these interactions like that, it can die out, it can take off as a movement. I'm fascinated with the Occupy movement, not because I'm participating in it, but because I'm wondering what's going to happen just because it got to be winter. What's going to happen next spring? Is it going to come back, or is it going to die out? And that's a real good example of an emergent phenomenon problem. And I haven't made a prediction, but we definitely had a winter in there that changed it. The German situation is interesting because in some ways, well, I think in many ways, there's a leap of faith. There is an assumption that they can replace nuclear. And that is, it's faith, it's not science.
Yeah.
So
That's
it's-
right, that's,
But as long as they're replacing it by buying power from French reactors, it's a little bit of a political move than an actual one.
well, it is, except what's happening now, though, is that they're diverting a lot of their federal, their dollars for research R&D in alternative energy. So you're right. I mean, it is immediately, and they're buying from somewhere else because they have those immediate needs. But I think it's a question of where they're putting the resources and what the consequences of this will be. It's an interesting thing to watch because in fact, can you make those kind of dramatic changes at the very highest levels in government, such that you can reverse the tide? Or, do you just have to kind of control this stuff, and then, it's going to happen because populations can continue to grow, and you just have to prepare for it? Or is there some intervention at that level?
Well, and that's why I think you can work, if you think of it as the emergent problem, you can intervene at different levels and try it out. You're not stuck at one thing. With the wise men and I would get really, really discouraged. I mean, this is inherently a depressing subject. The one hope that kept us going is that humans actually are capable of responding very fast when the right signals get sent or the right decisions made. And whether that comes from a bottoms-up movement or a top-down dictum, it may vary.
Well, certainly a good example of what we might call a positive tipping point comes from medicine. Let's say the initial invention of the smallpox vaccine, which
Right.
in the course of a very short period of time, as the technique of vaccination spread, eliminated a scourge.
You can be very cold-hearted and say, yes, every time you've had something that eliminates a scourge, you increase the population, so you cause famine. And there's a quite politically well-connected geologist, you both may know, Farouk Al-Baz. And he started a program called 10,000 Wells for Darfur. And so I was at a meeting, I said, okay, it's great, you're going to give water to all these people. But these people are going to go out there and have more people. And they're going to die in famine. So why can't you combine give the water for Darfur to the women and educate them about birth control at the same time? Oh, no, we can't do it. You can never win an argument with Farouk, I'm convinced. He says you can't let people die. But like with the smallpox vaccine or the water or the food supplies, we're in this very complicated loop. And humans are very creative. There's a species which is very...
But that's also dangerous because, you've got people like, not to get political, but Gingrich and things like that have these think tanks that think that we can engineer our way out of all these problems. And that's not the solution. I mean, we have the prowess to engineer our way out of some of this, but there is that human element. Where we just
that's
have to
why in
change
my world
perception.
body of things, there's that one part of it is the moral, ethical, political unit. There's kind of a UN that functions. Because it's just, it's one thing if you're on a small island, it's another thing if you're on a whole planet. Yes?
I'd actually like to sort of respond a bit to the idea that the gentleman brought up about contrasting long debate and with Germany taking this seemingly sudden step forward in response to Fukushima. And what comes to mind when I think about that contrast is that maybe there's not really, so much a contrast as two things that are always happening. I mean, my reaction is that I don't think you can take that sudden decision and totally remove it from the context of all the discussion and debate that has been happening, worldwide about nuclear power. For an analogy, because I love analogies, in my mind I think about a person who's jumping, and you never just jump without standing somewhere first to jump from. and having your balance and knowing where you are and getting ready to jump. And you're not jumping until you actually leap, but you can't leap without having had that context beforehand. So that's how I think of it with the phase of debate, and then it prepares you and gives you the readiness to, at some point, which maybe we can predict. I don't know. I'm not a social scientist, or maybe we can't predict. At some point, there's a trigger, and then you do jump.
So I think you're exactly right. And I mean, Germany has a very strong Green Party, that's for a long time. And so, when it gets close, it gets pushed, it's closer to its tipping point where something like this can happen. Whereas, there would be so much inertia to overcome for us to actually get to the point where we actually made such a radical decision. So, yeah, it would be very much dependent on whether we condition that particular society to accept that kind of movement.
My experience is something like that. I was thinking of it when Chip talked, but then your point consolidated. I was in the Martin Luther King March, the original march in Washington, and I think of that as a tipping point. But in fact, when you look what went on before that, it was exactly as you described. The foundation was there. The other thing that Alex and I were talking about at supper is that we were both basically grad students when plate tectonics was discovered. And again, that seemed like a revolution, but there was quite a long lead up to that, and then the right things came together. And that's why I had these...
40 years ago.
Yeah. I had these different movements and as examples, and I think that that's one of the points is that any of these actions can die out or take off. And it's not inherently predictable, maybe until you're really, really close to the tipping point.
So in these models, I mean, if you were to push it into, the right-hand model here, and then, yeah, I mean, can you back it off? And is there a spontaneous, is there this tipping point? Is there a tipping point in here where it doesn't return, or is there some inertia in this system such that you can go over that tipping point, but actually come back again and recover? So in this epidemic here,
Well,
and shrinking.
No, this wouldn't shrink. Well, this one would push it because you don't have any way to repopulate. I mean, this is
Okay.
really primitive.
Okay.
The way this works is you can do a bunch of runs, keeping the parameters the same. And what it tells you, what you see is that sometimes even when you're actually have your settings like this, you'll get that. And occasionally you'll get that. And then they have a whole statistical tool built in that tells you what your more probable situation is. And I tried looking at the grass, sheep, and wolf thing, and this is just something to play with. It's a weird programming language. It's not Fortran. So I was just playing with the available examples and trying to go in and change one thing in the program without messing myself up. So no, there's no way to recover from that. But there would be if you just had the right physics in the model, I think. You'd have to, well actually you would see it in the wolf, sheep, grass thing because the sheep can they have a birth rate in there. So, I mean, Iceland recovered after that 1783 Laki eruption. Killed off a quarter of the population.
Europe recovered after the Black Death, which also decimated the population by 75%.
It's interesting to look at what we consider these huge events, the wars and everything, on that population graph, and it's hard to even see a blip on the exponential curve. Yeah. You have a question?
So when you're talking about population here, you're kind of averaging out, but the population growth is different in different regions of the world. So depending on that, your tipping point may be different in different parts of the world, or what do you think?
Oh, definitely. Yeah, you'd have to. And we've seen that in some of the things that have happened with the island societies. And I've been traveling a fair bit in Africa where you have a very different situation than the US. And I mean, my husband actually lived in Africa a long time and can talk about the value of life. And when people's life expectancy is 40, they have a very different perspective on the value of life than we do when we expect to live to we're 70 or 80. No, you're definitely right. This is a generalization, but we are we are using resources from all parts of our planet. Some of us use more resources than others. The US and Canada are prime culprits in that. Europe. Australia is an interesting case to look at because they have a very pretty hostile country to live in, and how they balance their resources and their populations is different. And going way back and looking at the Aboriginals and how they evolved to live on that continent is just fascinating. There's a book by Tim Flanagan, I think is an Australian writer who has a fascinating story it's called something like In a Sun-Baked Land. A really good book.
So, going forward, what could we do to mitigate while also still continuing forward as a species, or is it just inevitable that we think we're going to have a catastrophe or equalizing event, kind of like Black Death?
Well, pandemics are always with us, always have been. No, I'm optimistic. I don't think a path is going to be particularly easy for a while. I have a 40-some-year-old son and a grandson, and I think the world's going to be a very different place in 40 or 50 years. It could be for the better, it could be for the worse. I am concerned about pandemics, but it may just be because it's something I don't know much about, so it's inherently scary. But, that goes back to biblical times. Maybe medicine is good enough, but we keep hearing about the immunities that these viruses are developing. I actually got the most respect possible for insects when I moved to Illinois. There's a corn borer. Okay, in Illinois, they rotate crops. You put corn here 1 year and soybeans the next, and you alternate them, and this keeps your soil in good condition. Well, this corn borer has figured out that if he's in corn, he's got to go lay his eggs in soy fields, or the next field where the corn will be the next year. And I'm not making that up. I actually talked to the entomologist. How can this bug have figured out that his cornfield's going to turn to soy the next year? It's just phenomenal. So, we're up against a pretty ruthless world out there. There's going to be some bug that's going to come and figure us out, and our antibiotics. So hopefully we can stay ahead of them. Yeah.
So you had mentioned that things like 9/11, Occupy, Arab Spring were results of this emergent system. And so do you think that the agents have changed, which we'll get to whatever our new model is going to be these things that pop up from the emergent structure and are consequences of that, or things imposed by like us, maybe the scientists who know the models? I don't know if I phrased that well, but
I don't think the models are going to get us where we need to be. That's why I said I think we can use the models as guides to statistically likely outcomes. But it's going to take a blend of physical sciences and behavioral sciences together, I think. And there are young people, basically, sort of grad student age people who are really seeing this and trying to actively get into the field of combining their physical sciences work with more of these social sciences, behavioral sciences problems. And I understand there are actually some grad schools now that are, I'm aware of one program at Stanford in particular, that are really trying to put all this together into training leaders for the future. So.
Is there some?
Yeah, human beings are great at changing, but only when we have to. Right? We're not great at looking forward and saying, I know I need to change. Kind of you were saying, the foresight's there, but we don't really want to do it that well. We're great at changing when we absolutely have to. When you started looking into this emergent behavior due to self-disasters and things like that, did you get a sense that the kind of ideology or the change that we're going to have to do is something that we will actually be able to do moving forward? Kind of you were saying people are going to do this and see that we need to do it and do it little by little, or we're going to sit and pontificate about it and talk about it amongst each other, making little steps here and there, but then when it really comes down on us, that's when people are going, whoa, everybody's going to start looking into how we can actually make these changes and affect things. So,
Yeah, well, I think you're asking is, does there have to crash before we'll change?
right, I mean, ultimately, yes.
I would say that it's hard not to imagine a crash, and I'll put it this way. Let's say, I mean, I call it the Al Gore dilemma, but it's my dilemma too. I flew here on a jet airplane. Okay. That is not a lifestyle that can be sustained for the average person if you average the whole planet. So am I being a hypocrite? It doesn't do any good if I wear a hair shirt or Al Gore wears a hair shirt, because it, you know, it's like if I recycle paper but nobody else does. So there's got to be some sort of collective vision, and hopefully all the internet and collectivity, and you people can see the world in a way that we never dreamed of when we were your age. It's just phenomenal, and I think that's the big hope, is that you can find out anything you want to know out there. If you just learn to be wise about what, you know, evaluate what you see on the internet. It's then the question is, my generation had to worry about how you even got that information. Your question is going to be, what do you do with that information? And I hope that people are wise enough. I just think, I worked actually in Oregon one year. I was doing field work up in Oregon, and I was headquartered in a Forest Service building. And this was, it was actually a place where I felt that if I didn't recycle my paper, somebody was going to know, because literally, if you put a piece of paper in the trash basket and hadn't used both sides of it, it appeared on your desk. I mean, there's like these trash ninjas going around just monitoring everything you did. Every light was turned off when you went out the room. Actually, they mostly had automatic switches. It was phenomenal, because you felt what you were doing at that scale mattered. And I think until people get that feeling that what you do as an individual actually really matters, and somehow it's enforced by peer pressure. I mean, there was no way to escape it in Oregon. That was it. I would never wear a fur coat. I don't wear fur coats anyhow, but I'd sure never wear one around there because somebody would have spray painted me with it. So I think there's peer pressure and wise leadership offer hope. I think it's probably a function of my age that I'm just pessimistic. You tend to be optimistic when you're young. I mean, I thought the Civil Rights March was the end of all problems in this country. It was such a glorious time. Well, it clearly wasn't the end of all.
Well, and I don't believe something, I guess, completely killing off this humans as a species is going to happen, but I feel like something pretty dramatic is going to be required for the globe as a whole to come together and say, well, these are problems that affect all of us, and we all have to work together, and I feel like it's going to be something pretty big for that to actually happen.
Well, and we're avoiding it. We're saying, okay, we're fine here in the U.S. Why do we care about Africa? Well, we ought to care about Africa as human beings. So, I'm sorry, I had another thought there, but I escaped. I'll come back probably tomorrow.
The problem I see is I feel like that's already happening. That those big things are occurring. That is a disaster, and we're blinded by things like the media and corporations that we don't really see the full picture. And I think it's already occurring now. And if we don't act soon, it could be too late. But while our generation has access to all that information, we're also blinded by so many distractions that are new to this generation, be it, movies, music, games, everything out there, that it's hard to pierce the veil and see what's actually going on, because there are all these problems in our world, and I feel we're slow to react already.
Well, I think that if you feel this tremendous sense of urgency, you're going to be frustrated, because it does take time. The question is, what can we do to help it along? The thing that I wanted to say when you talk about this catastrophe is that Tainter actually sort of defines what a complex society is. So and what I consider a catastrophe or collapse in that sense is the loss of the things that are our finest parts of our humanity, our cultures, the things we're building, the knowledge, the monuments, the things that are positive. And if you have a breakdown where one result is war, so he gets into a discussion of what's a collapse versus what's a takeover. Because if you have a weak neighbor and somebody else takes it over, that isn't necessarily a collapse. So I really recommend the book for fodder. It's just easy to read.
So you've talked obviously quite a bit about your tuning parameter and population. I feel like there are certain things that we can talk about somewhat dispassionately. If we're having problems with earthquakes, we can notice, look at this system of what goes on and say, oh, you know, huge number of people that are killed in earthquakes are killed because things fall on them. So we can engineer structures and try to deal with this major influence. With population, there's, you know, sensitivity. Like, you can't just jump out and say, okay, let's start engineering population, because then there's, you know, there's individuality and rights and all this stuff.
And yet some countries are doing that.
Are they doing it for environment though, or are they doing it because they hate the other people? I don't.
No, I went to, actually I was at a conference probably 20 years ago. It was before Al Gore was vice president, but he had written his book. He was an environmentalist. It was a conference that Francois Mitterrand in Paris convened. And it was global people, scientists and leaders, to talk about this. And what was absolutely startling was you could not mention population, because it just was the North versus the Southern Hemisphere. And guess what? Nothing's changed. You're right, it's still an issue that is very sensitive. And basically it was the Southern Hemisphere feeling we just wanted their resources and we wanted to tell them to have fewer people. And we couldn't get through that, and that's their perception. It's probably actually pretty accurate. So that's where we need the super United Nations.
No, I was referring to the sort of China's one-child policy, which has certainly slowed population growth.
Well, what I'm thinking about, what I'm getting to is that and this is not necessarily substantiated, but I have heard that the level of education of a population group can be a good predictor for the rate of population growth. And more educated populations tend to have a slower rate of population growth. I don't know if that's something that I just pulled out of some blog somewhere, or if other people have heard that as well. But if that is the case, it seems to me like education is something that we already give a lot of lip service to, saying we want to positively influence, you know, right, for education, let's fund it. How much we do, I don't know, but is this, you know, one more reason not to just be maybe patting each other on the back? I know we're all very into education here in this room, but to say that this is a palatable route to some sort of population engineering. Do you have any thoughts on that?
Well, I'm a little uncomfortable speculating on it because I'm not even a geographer. I'm really a geologist, and they're really sensitive issues. And actually, when I gave this talk at Illinois, some of the social geographers jumped in with questions very much like that. And I said, you know, I can't address that. It's just so far beyond what I normally am qualified to speak about. And one of the things that actually all my wise men and I got consistently was we're stepping outside of our role as earth scientists to get into territory. I mean, like I said, I would rather give a talk using lots of equations. I'm more comfortable giving a talk with lots of equations than this kind of talk, because it's very far from where my credentials are. And if anybody who disagreed with me and wanted to pick on that point can make a valid point. You have no training in this area, Kiefer. You know, you just... And scientists get in trouble all the way up to Congress, I think, when they testify and stepping this dual line. But I think we have to do it more and more, and I think a fair number of our colleagues think the same thing. And you know, we have expertise, but we're also human beings. We have concerns, we have desires to take action and to interact with our society.
You know, I think it also, I mean, ultimately comes down to this self-preservation. And at what point are you feeling as if perhaps, you or your offspring, or those things that you care most about are in danger of losing it? And it reminds me of interesting, I have a colleague, Monique Rosing, I don't know if you know him, but he's a geologist in Copenhagen, and he's worked on very old rocks in Greenland. He got a call from the Vatican, of all places, and basically the Vatican wanted to send a group of a priest up to Greenland, to the ice cap, and meet with scientists and talk about basically climate change issues. And so you had this meeting of the minds coming from completely different perspectives on the problem, but both of them understanding that our existence is threatened at some level. And you can see the same thing with sort of the Tea Party versus, the occupiers. When you look at some of the things that they're talking about, they aren't that far apart in some of their issues, and just kind of, somewhat of a, disdain for government and things like that. And you just wonder that that's what you got to do. You've got to get, it's a big circle, and you've got to get people with very different ideologies to recognize that in fact they have a common interest. And maybe that's what we have to do. We have to be pushed to the level at which we realize that we're not that far apart on these issues and that there's actually some common ground that's fundamental to all of us in terms of our survival.
About, I think it's 5 years ago now, I co-taught a sustainability course with the head of religious studies at Illinois. And we started an initiative, because I think that I'm not a religious person myself, but an enormous part of the world is. And I realized that's a place where we really can get to people's hearts and souls. And so we started a movement in Urbana-Champaign, where I live, of outreach to the churches. And it's actually grown really nicely. And very practical, largely evangelical churches. And I wanted to include the mosques, but everybody decided that was just a little further than we were able to go with this fledgling movement. But if that could really, and it's amazing how many of these people have become environmentally active in the community. And so I think there's a huge place for interactions amongst the churches. And then if the churches would just stop fighting with each other, we could make some progress. So I think it's going to take some really creative approaches, and a lot of them. And maybe some of them will stick.
Wasn't that the emergence? That it is a creative solution. I like your example of that you're working with religious groups who you shouldn't be working. Right? I mean, there's not a common vocabulary, there's not a common basis. That's where you're going to get emergent behaviors. Is that it's not a hierarchical, regimented sort of relationship that you have with people. You're exploring it, and it seems like that. If there's some sort of hope of a creative thing, it is in bringing together diverse kinds of agents, as opposed to say, like, these kind of reductions are, I mean, even though this is emergent, there's still this reduction of, like, human as alive or dead, or, you know what I mean? But I'm just trying to fish for some other kind of thing.
Well, and I think something came up.
The perception of how you can act, I think, is kind of in your thing, is like, it's that we're saying that what needs to change is the perception of your ability to act, rather than not that you can't act right now.
I think another thing that I would add to this is the basis of this discussion, and then maybe we can quit, is you need to try a lot of different things, and then hope that some of them.
And then again, it's emergence. If you don't just do one thing at a time, but you explore many things.
Multiple partial solutions.
Thank you for the discussion.
And on that note then, I think, we will have more discussion in class tomorrow morning for the people who are coming to class. And thank you again.
Recovery may be questionable, and these health disasters may lead to collapse. And there's Jared Diamond's book on collapse is very famous. There's one I like better because it's about a quarter the length, by Joseph Tainter, and it's called something like Collapse of Complex Societies. It's a really nice little book. So let's talk about some natural disasters historically. This is a chart of volcanic eruptions. They range in size from this one, which I've actually seen, 1 cubic meter that was erupted from a steam well in Iceland when a volcanic dike, a sheet of magma came through and happened to hit the steam well and the lava came up the tube and you had a cubic meter eruption. More relevant, there's Kilauea that erupts in Hawaii once every several months. Mount Etna, up to 1/10 of a cubic kilometer every 5 years. Mount St. Helens in 1980. Pinatubo in 1990. Krakatoa in 1883. And Tambora in 1815. And so here, we're down here, you're down here. Our grandparents tend to be in here. And my question was, what does the yellow box represent, if we look at the dates here? Anybody have a guess right away? It's the Industrial Revolution. So just since the steam engine was invented, these are the volcanic disasters that we've had. And on this slide, you can see the relation between what I'm saying about volcanoes and what we are seeing with population. So here's, I think the 1790s taken as the beginning of the industrial age. We've had, these are called volcanic explosivity indexes. They range like a Richter scale in earthquakes from 0 to 10. So 6 and a 7 is a fairly big but not the worst kind of eruption we've had. So 10s, where'd it go? Sorry, I'm going the wrong way. Okay, 10s would be Yellowstone, Hollywood type scale of eruption. Well, the reason I'm pointing out that the Industrial Revolution was important is that it's come at a time when we're really ramping up in this exponentially increasing population. The increasing density of population creates an increased density in the social fabric. So you're tied to you have a society that's tied together globally now, and an Earth that is going to keep on giving you this VEI 6 and 7 volcanic eruptions. And the point of this is that the consequences of those eruptions are changing because the interconnectivity of this society is changing. Well, what are the effects of volcanoes on humans? Well, if you're real close to the volcano, and in particular I'm going to use the concept of a tuning parameter. And that is some quantity which, when it hits a critical value, the system behavior changes rather dramatically. And the popular books, for example, that you might have heard of on this recently are The Tipping Point by Malcolm Gladwell and The Black Swan by Nassim Taleb. So the basic idea of this is that you have agents or entities that have rules that interact, and that creates something else at a bigger scale, but that has different rules of interaction that leads to new entities, and you cascade up the chain like this. So atoms interact to form molecules, which interact to form cells, which then end up forming organisms. And this word, as I think you've seen in the way this course has been designed by Alex, there are different characteristics and uses of the terms in different disciplines. And so where I come in is this talk is a blend of how we look at natural disasters in geology and stealth disasters more in a social science sense. And when I was doing some research for this, I actually came across some really interesting literature in the military literature about warfare as emergent phenomena. And is it inevitable? Are there characteristic timescales? And there's some really interesting reading there that I certainly never got into in my geology career. And so when I thought about this talk, the question was, does looking at natural disasters through the lens of emergent phenomena actually teach us anything useful? And that's the question I'm going to try to come back to at the end of the talk. Because if it doesn't lead us to anything useful, then this has all been an academic exercise. And a couple weeks ago, I didn't know what the conclusion of this talk was going to be. So it could have ended up as an academic exercise. So I'd like to give you an example of emergent phenomena using ant trails. And this is simulation with NetLogo. As I said, I've never done emergent phenomena calculations, but I really enjoyed getting into this and playing with it. So the idea in this problem is, it's a very simple problem. You have an ant nest in purple, you have 3 food piles in blue, and you have ants in red. And when an ant goes out, he leaves a scent on the ground, and that scent can disappear in 2 ways. It can either dissipate into the ground or it can evaporate. So those are your 2 control parameters. And then this just gets plugged into a simulation, and you find that if you have some extreme values of these parameters, model 1, where your diffusion rate's 50 and there's no evaporation, or in model 3, where your diffusion rate's 50 and there's a lot of evaporation, the ants can't find the food. But in model 2, where you've got these intermediate parameters of 50 and 15, the ants can find the food piles. So then you go play around in this more restricted range of parameters of model 2 and find out that there's actually...
Okay, I guess we can get started. And so this is the penultimate in our series of special distinguished lectures. And indeed, the last 2 distinguished lectures in the series deal with earth and environmental science. It's a great pleasure to introduce a colleague and a friend of long standing, Dr. Susan Kiefer, who's now at the University of Illinois. She's had a very varied and interesting career. We've known each other since we were both graduate students or postdocs, and really have collaborated on various things. Sue is trained as a geophysicist, and her interests have really, and contributions have really been very eclectic. They've ranged from mineral thermodynamics, in which she's done simplified models of the lattice vibrations in complex solids, and that was where I first got to know her, and indeed we co-supervised a graduate student, to thinking about fluid dynamics, thinking about what happens in rapids on the Colorado River, to thinking about what happens in plumes that come out of the outer planet, planetary moons, for example, Enceladus, to many other problems in geophysics where the physics, the chemistry, the fluid dynamics all come together. And she's similarly had a varied career in terms of locations. As I mentioned, she got her PhD from, or I didn't mention perhaps, she got her PhD from Caltech. She spent many years at the U.S. Geological Survey in Flagstaff, Arizona, a place where they trained astronauts, among other things. Sometime at Arizona State University, sometime at the University of British Columbia, sometime after winning a MacArthur Fellowship in Canada, doing various things in science education and other things, having her own company for a while, and then the University of Illinois. She and her husband have now bought a house on Whidbey Island in the Pacific Northwest, and that may be the headquarters for some interesting geophysics for years to come. Sue is also a member of the National Academy of Sciences and has served on many government committees and so on, looking at various areas of science and active areas of science and policy and thinking about education. And she's also a pretty darn good musician. So having said all of that, she's going to talk about natural and man-made, if you will, disasters, and what she particularly calls stealth disasters, and really emergent phenomena in how these things happen. Sue.
Coming out tonight. I've had the good fortune of having 6 wise men. 3 ways the ants can be eating. They can eat 1 pile, 2 piles, or 3 piles of food. And it's all very sensitive to the values of these parameters, whether the ants find food or not. And I really recommend this NetLogo because I'm not all that computer literate anymore, and I found it easy enough to get in that I could just change a few things and pretend I was doing something myself. Well, the problem is that was complicated when you only had 2 parameters, which were the diffusion rate and the evaporation rate. So you take something like another example in NetLogo where you've got wolves and sheep and grass. You've got things like, is the grass going to regrow and what's its regrowth time? You've got your initial sheep number, how much the sheep gain from food, and how fast the sheep reproduce. And you have your initial number of wolves, and how the wolves gain from the food, and how the wolves reproduce. And you get an incredibly complicated array of possible results. So my hypothesis is that many kinds of disasters emerge from the behavior of individual humans, which are the agents in this jargon, and that the tuning parameter is the human population, and that at some critical value of the human population, things may change dramatically. I can tell I'm in California because it's gotten dry. So here's how I'm going to define my disasters. And there's a continuum between these. So I take a natural disaster as what used to be called, or maybe still is, by the insurance industry, an afterthought. So it's natural. It happens pretty much in that non-bio part of the world. But it can be amplified by human behavior. So a flood in the Sacramento Basin here may not have been a disaster until humans started living here, and our behavior exacerbated that. Typically, natural disasters have a fairly sudden onset and immediate consequences. They make great newspaper headlines. There are historic examples, and remediation and recovery are often possible. So, in contrast, I'm saying a stealth disaster is caused by humans, but involves the natural systems that support us. They often have a gradual onset, so they don't make newspaper headlines very easily, but they have near-term consequences, years or decades, or centuries. And they're new to human experience, at least at a global scale. So if you're on Easter Island or any island society, you may have experienced these stealth disasters simply because you have finite resources. And the population can grow to be such that you use up your resources. But we're now in an era where we really are in danger of exploiting all of the critical resources of the planet. And in this case, remediation, in my career for at least 20 years, I call them my wise old men because they are all men, they are all old, and they are all wise. And they refuse to be co-authors anymore, so this is how I'm acknowledging them. And we've done various things of organizing symposia, writing papers on some of the issues of societal concern that don't really fit our traditional roles as geologists, but that we can't avoid seeing. I don't work on emergent phenomena as such, and so when Alex asked me to talk about this, I had to think, and she can talk anybody into anything. So this is a brand new talk for me, actually, and it gave me a chance to think about some things I've been working on in a new light. And so I'll tell you that I'm actually sometimes more comfortable talking about lots of equations and things than I am some of these ideas that I'm presenting, but they're speculative and they're meant to stir discussion, so I hope you'll take them in that spirit. So I'm going to talk about how I'm going to use the word emergent phenomena, and then I'm going to talk about natural disasters, and I'll define that using volcanic eruptions and earthquakes as examples. And then I'm going to define stealth disasters and talk about a couple of those, some problems when you dam rivers, when you deforest, and problems with soil. And then I'll talk about my conclusions and speculations. Now, I'm not going to talk about a whole bunch of hazards that fall under this category. Man-made hazards such as nuclear warfare, bioterrorism, nanotechnology gone wild, Alex. And I'll point out that if you are interested in things like that, there's this book by Posner who talks about a lot of these phenomena. Volcanic intrusion into a nuclear repository is actually something I did a tiny bit of consulting on. And then there's the, especially at the University of Illinois, I get a chuckle when I mention the high-energy physics experiment that might go awry. And don't ask me how, it's in Posner's book. And then there's some natural things I'm not going to talk about, including outbursts of charged particles. And when I gave this talk as a practice run to the geology colloquium at Illinois, it was like 2 days after a major solar outburst. And so I'll just point out that a solar flare and charged particle event. I lost the name of it. But this year and next year, we're coming into a solar maximum, and you might want to keep your eye on some of the phenomena that happen, because we've got a lot of things out in space and in our electrical grids that are potentially affected by these. And I'm not going to talk about big supernova explosions or big meteorite impacts, because we won't be able to do anything about those anyhow. So I'm going to use the term emergent phenomena in the sense of complex patterns that arise out of relatively simple interactions, and that the result of local interactions between individuals or agents leads to something that emerges at a bigger scale.